Hello, I want to talk about large-scale field programmable analog arrays. And I want to talk about them as being an energy efficient solution for embedded computing. And I want to kind of use this as a way to talk about not just what the concept is, but what the possibilities are in these devices. So I'm Jennifer Hassler. I'm at the Georgia Institute of Technology, and I would like to kind of go through these devices and talk about what we might see. Now, many people may be familiar with FPGAs. This is basically a combination of routing and logic with a whole bunch of inputs and outputs. Certainly is a concept that started in the 1980s. It really allows you to almost approximate, doing custom digital design. But what it really does allows you to, because of all the reconfigurability, you can kind of keep changing stuff. And you can even do it during field use of these devices. And it really allows you to have sort of code compatible kind of structures as a result. It's really interesting. You get a huge amount of routing, and that routing really gives you the configurability. But also that routing also is going to have some cost to it. And part of that cost is going to be in latency, which is not usually a huge cost, but it's there. In area, because if you just think you have many, many more switches, but particularly in energy. And in particular, energy is a big factor because of all the switches, but even more because to just even power the switches, I usually need SRAMs to power them, and they'll often take hundreds of milliwatts just to turn on a device. So we often see some pretty big issues there. Now with the FPA devices, it's very similar, except that you have analog elements as well. So FPA is a superset of the FPGA concept. But as we're talking about it for low power operation and things that can certainly be built in various infrastructures, as you can see below me, but also that you can use for very, very low power computation. For example, acoustic classification, where you talk about something going from input through the final solution. And this is important for any kind of technology like this, that this is an end-to-end solution. You might ask, well, what are different possibilities? And we get a nice long list. And what you notice with this list is it's not just saying, oh, look, I made an analog filter, which of course we can do. And that actually is a very important part. In fact, I can make several filters. In this fabric, which if you look at, you can see the circuit at the bottom, is actually both a mixture of analog and digital in sort of what we call our system on chip FPA design. But we were able to look at things like embedded machine learning that uses the time dynamics, because after all, I can build all the filters, I can build all the other pre-processing. Oh, and you can also compile the ADCs, but you're now talking about things like, neural architectures and various security aspects and analog computing. And all of these things have a huge energy efficiency in their process, as well as things like embedded machine learning that includes inference and training. So there's a huge opportunity in these kinds of structures. And you kind of look at this type of computation and you realize that, you can look at digital and look at its complexity like you might see for a typical numerical analysis class. Analog would be similar, except that unlike starting with, LU decomposition for linear systems, you're actually starting from differential equations. And this, and in fact, if I was going to solve a linear set of linear set of equations, I'd make a differential equation that converges to it like you see below. And what you find is that digital is really good for things that have good starting precision. So the LU decomposition aspect makes sense. It's also why when we think of digital, we think of this as a fundamental computation, which kind of corresponds to all the typical metrics like LINPACK and so forth. But in analog, as you have the really good intermediate numerics, although not this high starting precision. So you're going to do differential equations as your core computation. But there's absolutely no reason you can't sort of get a complete set out of either of these two approaches. And so that leads us now to this whole question of granularity, which in the previous results to some extent has been kind of figured out, but I want to kind of step back and talk about this because this turns out to be really, really important in terms of what is possible. Because usually when you think about granularity, you think about the picture towards the top of just having cabs and routing between them. Right. And of course, in FPGAs, you have SRAM and you have lookup tables, but you also have a couple other blocks and mixtures of elements there. And so what you find is you're left with an interesting question. Do I have, very, very fine grained granularity where maybe at level of transistors and I have a whole bunch of switches, but then the switches just like become this huge weight on the whole thing that even though I can get all this flexibility, and I want the flexibility because that enables the creativity of the designer, right? We want to be able to empower analog designers to find ways and creative ways to do things. The other alternative is to have some sort of larger blocks, maybe things that are already built, and that gets sort of connected through some other coarse sort of fabric. And we talked that this is more coarse grained fabric. And this works well, and you can kind of talk about pieces, but you're basically choosing from a menu of functions. So we might ask the question, how ideal a switch would we need? So the question becomes, the better the switch I have, the more I might think about fine-grained granularity. But even with that, I still need really good switches for any of these ones because the switches are going to basically just be assumed to be sort of extra overhead and loss. And so I can look at CMOS transistors and I have resistive loss. I have floating gate transistors, which are at least non-volatile, but still are going to have resistive loss, but some of the best, at least, options I'm going to get there. Certainly, if I do MESFETs and other 3.5 materials, I can do some things that are a little bit better. We could always talk about doing RRAMs and other memristor devices, but so that's going to be pretty messy and pretty difficult. And you're still going to have the same, you can still have a lot of resistive problems. You do get some interesting behavior with chalcogenides because you can get some really, really low resistive losses. It can also be non-volatile, at least binary, maybe a couple levels. And you could really see that being a really interesting technology for antenna, for certain RF switches on the front end. So if that's an opportunity, it would be great. But then the question eventually comes back to the things that we're looking at. We really would like to have fine-grained capability, but we really want to be able to have this at a far lower cost than fine-grained cost. In fact, we'd like it to actually be better than the coarse-grained cost. That might sound like a weird fantasy land, but it would be what we'd want to have. And so then you say, is there some way I can start talking about using the switches beyond being a switch? And that really does get us into the floating gate transistor concepts where the actual switch elements themselves, if done right, can actually be computing elements. And that sort of leads to the original conversation of switches are not dead weight. And so to talk about more on floating gate devices, what you have is you have these basically transistors with sort of basically a gate level material that it has no context on it. So that way things can be stored for a very long time. You're usually talking about 10-year lifetimes. That same transistor can be used for both computation and adaptation. You can certainly clear them. We usually talk about using precision program with hot electron injection and erasing with electron tunneling. And that allows me to be able to program millions of devices, to 14-bit accuracy routinely in the lab for students and so for people in various places way away from my own laboratory. And so this turns out to be a really big deal, but on top of it, floating gate devices are incredibly important for getting dense parameter systems. And because the next best option is to probably put a DAC at every parameter. And this works assuming you have only a few parameters, like maybe 10. But once you get much past that, even with like a 6-bit parameter, it's really hard to argue for not just using the floating gates for these kind of things. And if I'm going to build a system, it's really pretty easy to figure out which way you want to do this. So the question then comes back of what do we mean in terms of the fundamental computing and routing? And if you look at FPGAs and FPAs, basically what you think of them as having computing elements like CLBs, like computational logic blocks, and CABs, which are computational analog blocks, with a bunch of routing connected. And that's the general view. Now for digital structures, what you find in practice is that there's going to be a bunch of dedicated multipliers, a whole bunch of coefficient RAM, because again, I want to do matrix operation. Well, how is this going to work on the analog side? Well, here's where it gets interesting, because if I'm using floating gate elements in terms of the routing, these are actually still looking like crossbars. If I can use a single floating gate element where I can still program the charge in an analog way and store it still in a non-volatile way, I preserved my crossbars, which I know I can do things like vector matrix multiplication, but I can use them for all sorts of other transistors like synaptic elements or dendritic elements or resistive networks, or all sorts of forms of computation. It could be as very mundane as I need a current source, or I need something to help me set a DC bias, like the circuit you see below me, which is just sort of a typical capacitive amplifier, but I want to have, sort of a low frequency corner. This is something that one can very directly build and program into a structure like this. And these techniques are used in all these sort of areas and fundamentally enables a lot of analog design. Does it let you do everything? No. Does it let you do a large number of possibilities? And then we enable the creativity of the analog designer to go, I see ways I can use this, as analog designers always find a way on their canvas to find a way to make something work. It's kind of how this would shape up. And as a result, what we find in terms of the computation, in terms of the number of available parameters for, and you might say that that's related to computation, that these kind of fine-grained structures give you at least a good 1000x improvement, and is also enabled to build by far the largest Fpaa structures, as well as it has allowed us to ask questions about how do you make all of those components accessible? And that's actually been where much of the research has been over the many years, and then how to then build the tools around it. So some pretty phenomenal things you can do with this. And this kind of shows what the opportunities really look like in a real system. And on top of that, there's a whole range of partial high speed reconfigurability, because when the density is this high, you don't want to like take stuff and move it on to an off-chip memory and back, because that's actually going to be the primary cost. What you'd rather do is have all the structures available and maybe switch between them during runtime if you need to shift those around, because after all, you got to put a memory somewhere. It might as well be here rather than in some off-chip structure. And so to just give a sense of what the complexity and computation is possible here, if you have a CLB, it's typically going to be, say, maybe 8 LUTs on a very large structure and SRAM. So basically you're building simple state machines. It's a really neat structure. And it's really nice that you can have, when you have 10,000 of these, that's a lot of stuff to work with. Well, think about it on the analog side. Now I have the routing and the circuits, and what that means is in a single cab, I could actually have a small auditory classifier, and maybe even some of the signal processing for the subbanding structure, depending on how that's put together. This is all a result of the floating gate programming, and the fine-grained routing just gives you the gigantic capabilities. And again, part of it comes from just the pure analog having 1000x energy efficiency and 100x area, but this is actually a lot further beyond that, which could allow you to build sensor nodes that are pretty incredible, where you can have a front end stage, maybe operating 1 to 10 microwatts, that basically is just going to sit there always on and allow you to have sort of these context aware kind of systems on what we're putting together. And again, the point is always you're building end-to-end systems. If you don't have things that can build end-to-end and these configurable structures really enable it, you just have an algorithm that's not good enough, because it has to be what goes on for the full system. And in fact, one of the really interesting aspects of this is that you can imagine having near zero latency loops just running through the analog processing that's programmable and configurable. And then maybe I still have DACs and ADCs to kind of build stuff versus our typical low latency system, which really has to deal with an ADC, all the digital aspects, maybe an FPGA, and then shooting back through the DAC. And that latency can be quite significant in a range of applications over a lot of different spaces. Now, one of the other nice things about these Fpaa structures is that it gives you an opportunity to start thinking about, legacy and security questions. Certainly, what you might see below me is that you can actually talk about building unique functions and other sort of structures in the Fpaa, because you can actually exploit the fact that there is some aspects of mismatch, and you can work with it. Normally, we program those things out, but we can actually utilize them too, and that turns out to be quite useful. What you also see, just due to the floating gate elements, is that because I'm using floating gate elements in a particular structure, they're going, I don't have to worry about any SRAM vulnerabilities. The analog values you put on there are kind of tough to measure without disturbing. It is possible, but it is a little bit tricky. So if you're worried about like industrial espionage, it's kind of tough thing to pull off. the digital computing can actually get encoded as analog stuff, so that kind of even preserves that. And there's a lot of aspects, even you can build some self-destruct mechanisms if you're sort of a group that's so inclined to these questions. And the really neat thing on the FPA, and you can kind of see this, particularly the upper discussion, is that I can take this and I can take devices and have them come out of an IC fab that could be anywhere in the world because the components are fairly generic and fairly straightforward and published and just people know, just like FPGAs. And it's a generic and known structure, but when it's done, what you find is, okay, I can actually take it to some sort of safe location where maybe I'm putting my secret sauce for my particular company into the fabric. And I can also verify to make sure in case anybody did anything weird to this device, I can always just be sure to make sure that my customers are fine. And when it's all done, I can actually just say, here's my specific, IC product that I'm giving that has everything, that I can be very certain of in terms of a quality of assurance to whoever the customer might be. And what we realized is that FPGAs really were a major force in solving the sort of digital design in terms of security, but also legacy. So once you had a VHDL code or Verilog code in one processor, you could move it to another one. And so the same question is, can this be done on the analog side and the mixed signal side? And the answer is that probably yes. And in some cases it's worked well, and there's probably a lot to still keep asking in terms of as this continues to roll out for analog parts or the whole analog system to kind of encapsulate it into one place. And there's a huge number of opportunities in terms of understanding this for really, really low power nodes, for really low memory nodes. And security tends to be much better when you actually have fewer possible sort of open holes or layers in an infrastructure. And so there's a lot of opportunity you have in that space. Then you start to ask a couple more interesting questions. And one of the big ones that comes out is asking the question of, with FPGA devices, how fast could they work? Or also what IC processes? And what we find is you go to smaller IC processes, you do scale the amount of things that are available on a particular process node. You also increase the operating frequency. And that's probably the latter is probably one of the really big reasons you do want to scale, because then you can get into a wider range of applications in addition to having more capability. So that works well, although there certainly are, as you scale down in process nodes, you obviously have issues to do that. On the flip side, you also get a lot out of very old nodes. A lot of the core structures have been built in 350 nanometer CMOS. There's a lot we can do still in 350 nanometer CMOS that still is competitive or sometimes better than devices built in 14 and 7 nanometer. And the economics of that is rather dramatic. Now, I imagine any of these circuits going forward, there's going to be some interesting questions that you would have. One of which is going to be, you're going to have you're always going to need some specialized parts. So if you need to handle really high voltage, you're probably going to maybe have a part that's right on the outside edge of it. That may be, a 3.5 or a gallium nitride device that can handle maybe the really high frequency or the high RF power. And ideally, you'd like to be able to have those be configurable, and maybe there is a symbiotic seam that connects to all of these things. These maybe become peripherals that you build that. There may be other sort of specialized components on a chip or around that, or even devices to do like higher, high current output currents and so forth. But what it does allow you is it gives you kind of sort of the center to kind of then, even if you have these kind of things at the edges, you can kind of put them and utilize them where you need them, and probably actually increases the opportunities of those spaces, doesn't decrease it, just because of all of the increased opportunity. And the other thing that's nice is you get huge programmability over a wide range on these devices. Even looking at things like ladder filter lines that you could imagine doing, certainly show this across 2 technologies, but you could imagine this being done, even a whole range of this, even in one technology, with the fact that floating gates can get programmed over 7, 8 orders of magnitude of bias current. And that really is a huge opportunity for many of these cases and opportunities. So then you ask a question, well, how does the scaling on this work, right? Because we sort of mentioned that's possible. What could we imagine to expect? Because we see these FPAs at a certain size now, but how are they going to grow up in these larger technology nodes? And one way to look at it is, well, what's the number of cabs or CLBs? And maybe now we're sitting at 200 to 400 in, say, a 350 nanometer CMOS. And there's certainly been things done in some of these other nodes, which is one of the reasons some of these are picked. But what you can see is that the number of cabs very quickly starts to move into cabs or CLBs, starts to become 100,000 at a 14 nanometer process. This starts to become rather significant. You might say, well, how would that compare to sort of like LUT or LUT equivalents if I did a purely digital? And you start to realize, well, at 14, you're sort of sitting at that sort of 100 to 100 million gate equivalent. Largest FPGA one is like 20 million. So you start to get a sense of, all right, but that's probably pretty expected from a number of these structures. Gate equivalent is a very fuzzy metric, and that would be a whole discussion and talk in itself. Fair enough to say, no problem getting to sort of that complexity without any trouble. But then the interesting question is, remember, we can talk about doing vector matrix multiplication in any of these computational blocks. And so you can start saying, well, let's assume I can get maybe 12% of the devices I can use for VMM, which is maybe a low number, but practically when you hook up stuff, you might see this. And you look at that number, and the current structures now, we're just a little under 100,000, which is still pretty cool. But as you start to get to like a 14 nanometer node, you're talking 10 million. If you start to go, even smaller, now you're starting to talk about, in the 100 millions of ranges, which means that, say, VMM is the core thing in a neural network weight. You're now talking about some of the largest neural networks that are built today for anything, any of the structures. The largest one today is right around 100 million weights. And so so you're saying I could do this in a single 1 centimeter by 1 centimeter chip that would be running at a reasonable level. So a whole supercomputer is in a chip. It's a pretty amazing concept. Take it another sense, you can imagine what happens when I get when I look for the really low energy aspects at 1 microamp and 1 milliwatt and 1 microwatt kind of power levels. 1 milliwatt is kind of the battery powered level. The 1 microwatt level is like, simple energy harvesting. I don't even have to think about it. Even at 1 milliwatt, I could use energy harvesting in these structures. And you start talking about, say at a 40 nanometer process, 1 microwatt, you can start to be talking about one gigaMAC per second, which is usually better performance than most laptops today, in a power that's basically throwaway. And at 1 teramac per second, which is basically a GPU cluster, again, also sitting at about 1 milliwatt of power that could be either energy harvest or battery power that could be sitting in your cell phone. There's a huge amount, and then as we scale, it gets even better and better. So the opportunities here are rather incredible from a low power perspective. And we can then start to go into interesting questions of, well, how much computing can we have? And it's not hard to imagine getting to, computing numbers that start to become rather amazing, both allowing us to do some amazing RF processing as well as being able to do image processing, making the image processing almost looking like large GPU architectures, but it's all analog GPU and extremely low power. Pretty incredible kinds of devices in all of these ranges. And just to get a sense, you start talking about your 1 petaMAC is a typically good size supercomputer. And we start talking about on single chips being able to do, factors of that. So you could just imagine now what the possibilities could be as we start to build and scale these structures. I would be remiss if I didn't say that there are tools, because tools is kind of like one of the key things that drives this whole conversation. And there are sort of high-level tools that have some high-level abstraction and work your way down. And this has been used for a whole range of things. One tool set to simulate, target, and design, been used at classes at Georgia Tech. This particular set's been used for over 5 years. And there's a whole flow to this. And if you think a little bit, there's actually some interesting opportunities in other automation around this conversation. And the last part of this is also asking, okay, now I get all of that computing. What does this look like in terms of computing with analog quantities or analog, and now we're talking about computing with real values. And so now the question is, okay, if I'm computing over reals, and now I can have connections like, all the other neuromorphic computing, but also quantum and optical sort of structures, has a huge opportunity, and you can, and to be able to compute things that digital systems are really going to struggle with. And part of what makes that work is the fact that you do have sort of numerical analysis and architectures and abstraction, like what digital's had for a long time. But now you can start to talk about that computing over real values, like Turing machines over real values versus over discrete. And allows you, and then the question is, well, what are the opportunities? And there's some huge possibilities. It's still somewhat speculative, but I think we're going to find some interesting opportunities going forward. But here's the thing, what could FPAs look like in the near term? And we'll often start to talk about an FPA, oh yeah, this is what the technology, what it could be. Or what is the, we'll say, this FPA, these FPAs could be of this kind of complexity, well, or this kind of capability. Well, you might ask, well, what does this mean? And in that case, we could talk about, from all the scaling discussions, what some of those simple metrics might look like, both from, say, a 350 nanometers, maybe a little more optimized than what we have now, but pretty much all those numbers are exactly what we would expect, to what a 130 nanometer structure, to a 45 or 14. And when we talk about what is like the capability of the FPAs going forward, you want to look at the 45 nanometer to 14 nanometer, that would be what this would mean. And obviously developing this has really been relevant in terms of discussions around synthesis. It allows us to kind of talk about this. That's a whole nother conversation, but a really important one in terms of giving us the grounding of why these numbers are where they are. Also understand in practice, a commercial source would have a family of devices and probably have some programmable, configurable peripheral devices either in the package or somewhere there, or there'd be also an ecosystem of other companies being able to say, oh, here's a peripheral that fits into that. So like a company that's really good at gallium nitride for certain RF or power devices, you might imagine that would connect. And so all of that's really important, but it rests on having this core infrastructure. So the opportunity of these devices is huge, and the possibility going forward is pretty remarkable. As we talk about these devices, I'm just kind of in this table, it's like a 5 millimeter device. There's really a lot of opportunity going forward. And this is where we want to sort of start the conversations and kind of see where are the opportunities using these devices going forward.